limit select as k1 by 1. But for the rest, for the other test, this one we can easily ask if used to produce the result of the test. Okay. So the other available tests are Lagrange multiplier and test. So let's consider the model to be like this. So we have dependent variable and a number of independent variable, and then we have error. So where the error variance is given by the expected value for this birds. So we have a number of different tests. The first one we call as a Brush-Pagan-Godfrey test. This test is basically used to identify if the error variance is proportional to any of the x. Okay. So we have many x in the model x. So it's possible that any of these x produce the problem of heteroscedasticity error variance. Just like before lah. So it's possible that any of x that we have in the list of independent variable produce this kind of spread, different spread of error variance. Okay. So maybe we have one. It's possible we have more than one that produce the problem or the source of the problem. Okay. So basically again, the first test, the Brush-Pagan-Godfrey test, it can be used to identify if the error variance is proportional to any of the independent variables. Yeah, it depends on the value of any of the x. Okay, it depends on the value of any of the x. So that's why we got proportional. The error variance proportional to any of the x. So basically, we want to test. We perform in order to identify the one. Okay. And then we have another test, lateral test. This one is used in order to identify if the error variance proportional to the square. The error variance proportional to square of any of x. Okay, this one just x, but this one square of x. This one, the error variance proportional to square of any of x. So we know that just now I explained to you that there are many patterns of heteroscedastic error variance. So basically we can use different tests in order to identify the different pattern of heteroscedastic error variance. So this one is can be used the best to identify if there is the error variance proportional to the exponent of any of x. Okay, so exponent of x. So this one we call Harvey test and test. So for the null hypothesis, we are testing whether the parameters, the coefficient or parameters for each of x, for any of these x, if all of x equal to 0, or at least one of them not equal to 0. If one of them not equal to 0, meaning that the error variance depends on that x, whether it's proportional to x or proportional to the x squared or proportional to exponent of x. Okay. So we test the coefficient here. The null hypothesis says that all equal to 0. So if all equal to 0, then the error variance does not depend on x. Okay, does not depend on x. If we reject, means that it depends on any of x. Okay, any of this not equal to 0, then it depends on the error variance. The value of error variance depends on the value of x. Yeah. But because we do not know the error variance, then we use the estimate obtained by applying the radius square to the model. So we use estimate of the disturbance for the error variance. Okay, so basically we use the residual. So residual is used as estimate for the error term. So for the Brush-Pagan-Godfrey LM test, it involves a number of steps. So the first step, estimate the model by the radius square and obtain the residuals, and then run the following auxiliary regression. So you regress the square of the residuals Okay, so the estimate of the disturbance U, we use a residual estimate for the U. So we, in order to perform the test, you regress the square of the residuals, and then regress against all independent variables. Okay, regress against all the independent variables in the model. Then the next step, compute the test statistic, which is given by sample size times the R square from this one. The R square from this model, not original model, from this equation after you estimate this one, not for the original one. So where n and R square are from the auxiliary regression. So if your test statistic greater than the critical value on the chi-square table, dia provide chi-square table, stable chi-square table. If the test statistic you calculate here greater than the critical value, so P is number of your independent variable here, the number of x you have here that determines the degree of freedom. So if the value of test statistic greater than the critical value from table, and then we reject and conclude there is heteroscedastic error variance. So meaning that the error variance depends on being influenced by the value of x, any of x lah. So to perform this test, okay, so now this is the model. So let's say we estimate using all data, so 1 to 18. Estimate the model, R&D expenditure, spatials, using all data 1 to 18. Okay, this one, if you use EViews, you can easily get the result of the test. Okay, but later I will show you how to, how that the test statistic is obtained. So I will show you later on. If you do it manually, then you understand how it is obtained. So if you use EViews, for example, I mentioned earlier for the midterm test. For example, if I ask you to perform the test, then you do not need to do the manual way. You just use EViews to get the result, and then you just interpret the result. Okay. Although in lecture we discuss the manual way, that to help you to understand how it is obtained, where it is obtained, how the test statistic is calculated. Okay. So what you need to do, you just estimate the model, and in order to get the test statistic as well as the p value, you just go to view, residual diagnostic, and then select heteroscedasticity test. Okay, so we have a list of available tests. We can, the first one Berbagan, and then we have Gletzer, second one, Harvey, Arch, White. So this one we discuss later. So we do the first one first, the Partner Cochrane. Again, this one is the test to be used to detect if the error variable proportional to the x, any of x. Regresses is self-optimal. So okay, and then you get this. The F test statistic 4.187 something, P value 0.04. So if you perform the test at 5% significant level, then we reject the null hypothesis. So the null hypothesis, as given earlier, we are testing the coefficient in front of each of x for all slope parameter in the auxiliary the auxiliary equation equal to 0 or at least 1 equal to 0. Okay. So this one we reject, meaning that at least one of them not equal to 0. It means that the error variance is proportional to x. Meaning it depends on the value of x lah. The error variance depends on, it's not constant, but it depends on the value of x. So we conclude that the model suffer or has the problems of heteroscedasticity. Okay. So how we get this value? The test statistic is done by regressing the square of residual against all x. In this case, our example, we only have one x, we only have one L, which is the sales. So we just regress against sales. If you have more than one x, let's say you have another x, then you have to regress, you have to include the x as well in the model. So this value is obtained by regressing the residual, this one, residual. So maybe we can save the residual first. After we estimate this one, we have residual. This one residual, residual. So residual, again, the difference between the actual minus the fitted values. So we have so residual is the estimate for this one. So the first one is an estimate for the first disturbance, and then second and so on. Estimate for this one, estimate for the disturbance or the so the residual, this is what we call residual. See? So residual is the estimate. We call it residual. Okay. So maybe we save this one first in order to perform the test. You go to, because every time we estimate a model, this one, the receipt here, it will store the latest residual. I mean for the latest model we estimate, for the last model we estimate. Okay. So let's say later you estimate the model, then it will keep the residual for the last estimated model. So better we save this one first, residual produced by the model. So you go to quick generate series, and then let's say you put u equal to receipt in order to save the residual of the first model, okay, in the a new variable called as u equal to receipt. Okay, so now we have the residual is saved here. So now we can so now this is the one that produced. I mean, we asked EViews to produce the result of the test, but how this value is obtained? So it's obtained by regressing the square of residual against all x. But in this case, we only have one x, which is sales. If let's say your model has more than one x, you have to put all x here. Let's say you have sales, and then you have other x2, x3, and then you have to put all. Later we have example. Later we have exercise. We have one example where we have 2x, and then how when we have 2x, how to perform the test. You have to include both lah. So this one, you go to quick estimate equation again. So you have just now you have. This one you have to regress the square of residual, which is u squared, and then you have c, and you have all x, but we only have one x here, sales. So this just to help you to understand how the test statistic is obtained, but we are only able to get the test statistic, the p-value, we don't have that. So if use to produce the result, then it provides the as well. This one just to help you to understand how do we get this one 4.18. It's obtained by guessing the square of residual against the independent variables, and then we get the R square, and then you multiply sample size times the R square. Okay, so this one, okay. Equation 1. So now we have the R square 0.23 something. Your sample size n 18. So 18 times this. So it's equal to the the characteristic that we have just now. So this one 4.18, which is the same to the one produced by the user now. But this one, if you only have this one, then you have to compare to the critical value property to form the chi-square table. You have to refer to price table, chi-square table, degree of freedom 1, let's say 5% angle level. So 3.8 for 1, so this value greater than this critical value. So reject. Conclude that the error variance depends on the value of x. The error variance depends on. So there is heteroscedasticity problem. So there is heteroscedasticity error. Heteroscedastic error variance. Okay. So second one, the other available test, the one we call as Linzer test. So the step almost the same. Only difference that this one will regress the absolute value of the residuals, because residual can be positive, can be negative. So we convert using absolute value. So absolute value of residual against all x. So again, this one is the best to be used to identify if the error variance proportional to square of x. So it means that we have a number of different tests. So not all tests will be able to identify the problem. So let's say the model has a heteroscedastic problem, but remember that heteroscedastic error variance has different types of vectors. So that's why we have different model, different approach that we can use, because sometimes one test unable to detect the problem, because the test is the best to be used to detect different pattern of error variance. Our use is unable to detect if the error variance are not what is supposed to be detected. So for this one, the estimate model get a residual and then regress the absolute value of residual against all x. Again, for this example, when you have one x, which is sales, and then you get the R square, calculate sample size times R square, compare to the value from R square table. So this one, if you go back to the earlier model, equation 1, this one the original model that has the problem. Okay, the model that has problem. You regress R and D exponentials against sales, space sales. To get the result of the test, you go to view, residual diagnostic, heteroscedasticity, and then select the one, select the test that gets show you the performance correctly. Okay. This one, the third one. So you press OK, and then you get this one. Test statistic 4.217, and then p value 0.04. So again, you use 5% critical level, then it is less than 5%. So we reject, conclude that the error variance depends on x. In this case, sales depend on sales. So means the value of sales influence or makes the value of error variance to be different. So for this one, how we obtain 4.2? It is obtained by regressing absolute value of error against the independent variables. So if we redo that one, so I think this one, we re-estimate this one, estimate absolute value of error ABS square U and then species specials. Okay, so you get the R square, you have n sample size 18, 18 times 0.234 something, so you get 4.217. You don't have any value, then you compare the value to the value from T from chi-square table. If you are not able to know how to get this one, you ask me later. So basically it's not that difficult. You just open the chi-square table. Okay, sure. So this one 5%, 5%, 0.05, degree of freedom 1. Degree of freedom, how to know how many degree of freedom? How the degree of freedom, it is the number of regressors you have. The number of regressors you have in the testing equation. So you only have cells, so only one. So it's 0.05, 3.841. So this one greater than critical value, reject. So conclude that there is heteroscedasticity problem. So the value of error variance, regression error variance depends on the value of cells, depends on the value of x. So it is proportional to. So in this case, proportional to the x, to the square of cells. Next one, we have, so just now we discussed this one, there's a Harvey and test. So the next one, I mentioned before, this is suitable to detect if the error variance proportional to the exponent of x, so this one we call as the Harvey and test. The steps are the same except that we regress log of square residual against the x, So this one log of the square residual. Okay, so we ask if used to produce the result first. We go back to equation 1, the original model. So how to get that result? You go to view, residual diagnostic, homoscedasticity test. You select second one, Harvey. Okay, so you get one 94. So this one, because this one you conclude that there is no heteroscedasticity. This one because p value greater than 0.05, so we do not reject. So meaning that the error variance is not proportional to the exponent of x. So what the first two tests suggest there is heteroscedasticity. So meaning that you can see that now this test unable to detect that the error variance is not equal. Error variance is not equal, it's not the same for different operations. But this test unable to detect because it is used to detect for different pattern of heteroscedastic error variance. So but in this case it has different pattern of error variance, but this test basically used to detect different other types of error variance. homoscedastic error variant. So it failed to identify problem. Actually, the model suffered the problem, but so this test is able because it tests different pattern of the heteroscedastic error variant. So how we obtain 1.94? It is obtained by regressing the log of square error. So you go back to this one. So we re-estimate. It is log of square error, log. Log of square residuals, and then regress again C and C. So okay. So your n 18 times 0.17, 1.07. So you get 1.942, which is equal to this one. So this one, you compare the integral value, because this one is smaller than this, you do not reject. Okay, so test is smaller than the integral value, you do not reject. So based on this, you say that there is no heteroscedastic, but basically the more accurate interpretation is that there is no heteroscedasticity error variant as what we call that that is what the test is intended to test. Because remember just now I explained to you, the Harvey test is used to identify if the error variant is proportional to the exponent of x. Okay, but the model has different types of heteroscedastic error variant. It has the problem by different types of the pattern of the heteroscedastic, not what they're supposed to detect. Okay. So conclusion, there is no, but basically the model has the problem. Okay, and then another one is the Ingle arch test. The Ingle's arch test. The Ingle introduced a new concept allowing for heteroscedasticity to occur in the variance of the error term rather than in the error term themselves. The key idea is that the variance of the error term depends on the size of the squared error term lag one period. So the lag one period means the previous value of the error term for the first order model, or as given here, so the variance of the error term depends on the lag one of the square of the error term or residual. We can use residual as an estimate. Okay, so meaning that it depends on the previous variance, the previous value of variance, not based on x, the value of x, but the previous value of variance determines the error variance for the next error variance. So the model can be easily extended for higher order by adding more lag of the square error term or square residual. When we implement it, we use the estimate. We use the residual as estimate. So the step, the estimate model and obtain residual, regress the square residual against the lag of square residual. Okay, lag 1, lag 2, lag 3, and so on. And then you compute the test estimate, which is given by sample size minus the order that you are testing. In the first order, the minus 1. Okay, and then time that square from the model, and compare that value to the value from table, and then make conclusion whether to reject or not to reject. Okay. Okay, so this one, you go back to the equation 1, the first model. How to get that the result of the test the what we call that Ingle's arch test, the arch test. So you go to view residual, then stick heteroscedasticity test, select arch. So this one nampak pula, you are testing for the first order only, that you believe, you are testing if the current error variant depends on the value of the previous variant only, like 1, then you just put 1 lah. So you want to consider for higher order, for example lag 2 as well, you put 2. Okay, for the default lag 1 lah. Okay, the default setting just lag 1. So it allows to test if the previous value of the variant determines the next value, the current value. The previous value determines the current value of the variance, error variance. So okay, so you get is 2.019, p value 0.145, which is greater than 0.05. So we reject now. So meaning that there is no. Again, there is no heteroscedasticity, but no heteroscedasticity based on the tested hypothesis. So basically, we are testing if there is error variance depends on the previous value of variance. Okay, not based depend on X, but depend on the previous variance of the error term. So it is good that you perform a test using different tests, but if you don't want to use many tests, you can choose lah. But again so basically in terms of different tests have different probability of making for us to make incorrect conclusion. Okay. So this one, how to perform the test? We need to regress. So this one we need to regress the square of residual against lag of the square residuals. So this one you need to have a square residual first. This one is residual, so you need to have square of residual. So you go to quick generate new series, quick generate new series. Let's say the square of residual you put U2 represent the square of residual, so you put and then equal to U square. Okay, now you can perform the test. So this one you regress, U2 against Cn squared of U2's lag 1. So the first order, so U2 space C space U2 bracket minus 1, so lag 1 the previous value. Okay, so you get your n minus 1 is now n minus p, n minus p, so n minus 1, 17 times this one, 0.1187, 118781, so you get 2.019, and then this one smaller than the predicted value from table, so no reject. So based on this test, we conclude the error variance is not proportional, it not depends on the previous variance of the error term. Okay, and then we have one more test, the one that we call as the white test. So this test allows us to test if the error variance depends on any of x, or square of x, or interaction between x. Okay, so we have this one is more flexible, so it allows us, but it has, because it allows for many regressors in the model, so it is less reliable as compared to the other test that we discussed earlier. But it allows us to test different pattern of heteroscedastic error variance. Not only whether error variance proportional to x, but whether error variance proportional to square of x. So many combination of the first two tests lah. Okay. And then in addition, it's allowed also to test whether error variance proportional to the interaction between x. Okay, between two and each pair of the x. So the tests are quite similar. So estimate, get the residual, and then regress the residual, regress the square of residual against all x, and then the square of all x, and then the interaction between x. And then you get the R square, calculate the test statistic, compare with critical value, and then make conclusion. Okay. So P, number of the critical value depends on number of regressors you have in this equation. So again, we go back to this one, we go back to this, the equation 1, the original equation. So you estimate the original model, you go to view, residual diagnostic, heteroscedasticity, select Y. So include cross term. What cross term means? The interaction between x. Okay, so interaction. You don't want to include interaction, you can unclick this one, but this one we just perform the test by adding the interaction as well. Okay, so you get so test statistic 5.17, p value 0.07. So if you perform the test 5% level, then the conclusion is that there is no problem of heteroscedasticity. But basically, you perform the test using other tests, then we conclude there is problem. But because this test allow us to have many regressors, so you can produce different conclusion lah. So meaning that you can perform the white test, but it allows for higher possibility of making incorrect, for example, incorrect conclusion. So we conclude that there is no problem, but the reality there is a problem. It is a problem. Yeah. So in this side, basically it is acceptable. Some you get to the article, for example, some they just perform white test, but it's just like the COVID-19 test lah. You use different test kit. Some test kit are able to detect, but other test kit are able to detect. So that's the risk lah. That's the risk of using different tests. Okay. How we obtain this one? It's obtained by regressing